Today we're going to be working on symmetry. So what is symmetry? Right, so if you have a line of symmetry, that means that's a line you can fold the graph over and it'll be the same thing on both sides. You're going to finish your match, and put it up. Okay, so it's saying what transformations can be used to help map the figure onto itself, and then why can some figures be mapped onto themselves? You can see we've got this strange looking, what do you say it looks like? A what? Ninja star, that's what I was thinking. It's a ninja star. I don't know if y'all knew what a ninja star was.
It's things you throw.
Okay, so why can some figures be mapped onto themselves? Well, a figure has symmetry if rigid motion can be used to map the figure back onto itself. So the first one we're going to look at is reflectional symmetry. This is a symmetry for which a reflection maps the figure onto itself. The line of reflection for a reflection symmetry is called a line of symmetry. So, again, think about it. You've got line M here. If I were to reflect this image over line M, it would still look exactly like itself, right? Or kind of like Grayson was saying, if we fold it over that line, am I going to have the exact same figure? Is it going to line up perfectly? And it will. So that's called reflectional symmetry. Right, here's another line N, that if I were to fold over line N, it folds exactly on itself. Another kind of reflectional symmetry. It says the reflections R sub M and R sub N map the figure onto itself. Observe that lines M and N both divide the figure into two pieces with the same size and shape. So that is reflectional symmetry and lines of reflection. We also can have rotational symmetry. This is if an image is mapped onto the pre-image after you rotate less than 360 degrees. So what they're saying is, if I look at this image, if I rotate it less than one full rotation, right? Because obviously if I rotate something all the way around, it's going to look just like its original. Okay? Can I rotate it some amount and make it line up exactly with where it's at now?
Yes.
Yes, for this one, how much would I have to rotate it?
360.
But we want it to be less than 360. If I rotate 360, you're right, it'll look exactly like this. But can I rotate something less than 360 and make it match? 180. So what if I rotated this corner and put it right here? Right, and imagine rotating that. Would it be the exact same figure if I rotated 180?
Yes.
It would. So because I can rotate it some amount and make it look exactly like itself, then it has rotational symmetry. So those are the two kinds of symmetry we're going to be focusing on today. So look at one. Now, I want you to talk about, on your paper, what kind of symmetry do each of these have? So they're saying, what transformations can you do? So basically, can I reflect it, which means fold it in half, and could I rotate it and make it have symmetry? So you're telling what kind of transformations would work for A and for B. Okay, so when we look at A part, did it have reflectional
Yes.
symmetry? Okay, what could we reflect it over?
You can split the small little ones in half and it'll fold that way. And if you did that,
Like
it'd
this?
make like a top hat shape.
Like that? Okay, so top hat, A blinking. I see it.
And then
You
you do
fold
the
it
same
off.
thing with the line piece and make a.
Is it this way too?
I'll go with that.
And you can rotate
So it has two kinds of reflectional symmetry, right? So we call those lines of reflection. So we could reflect it over a vertical line through the center,
You can rotate it too.
You could reflect it across a horizontal line on the center, and you could rotate it. How much could you rotate it?
180.
180.
180 degrees. So we're going to say all those. So we could reflect over a vertical line, which would be this one here. We can reflect over a horizontal line. This one here. And then we can rotate 180 degrees. Right, all three of those. Okay?
Point.
Any questions on A? Okay, what about B? What kind of symmetry do we have there?
You only
Rotational.
reflect it down the middle.
What kind of line?
Vertical.
Vertical, right? Vertical line. So if I fold it over that vertical line, the eyes will fold on top of themselves, the mouth will fold on top of itself. So I agree, we can reflect over a vertical line.
We rotate. Rotational. Yeah.
But it has to be less than
180.
360.
Do 180.
So if I rotate 180 degrees, do I have the exact same figure?
No, you have a sideways.
No.
No, you have an upside down small face.
It's always my face. Same thing.
If you rotate it 180 degrees, it would be upside down. Like that.
So does this map exactly on top of it?
No.
No. So 180 degrees rotation does not work. Because it has to map exactly, if I rotate it, it has to line up exactly over the top. But the smiley face and the eyes would both be in the wrong spot, right? So can't rotate it. Right, what about a horizontal line? Would that work here? Could I fold over a horizontal line? No, because the eyes would fold on top of the mouth, right, and that wouldn't work. So here the only thing is a reflection over a vertical line.
So if you can't rotate it, you just don't put it at all?
You're just saying what kind of symmetry it has. So they're not all going to have all the kinds of symmetry. Some of them may just have some. Okay, so now then we're going to be counting up how many lines of symmetry each one has. So we're focusing now mainly on reflectional symmetry. Right? Can I reflect it or fold it over this line and it fold exactly on top of itself? Okay, so when you look at example 2, you can see through every vertice of a regular hexagon. Okay, what is regular? Does anybody know what regular means?
Like the normal shape, like that, the stop
Yeah.
sign maple shape.
So in order for a polygon, so for any shape to be called regular, you have to have all sides equal. So if that's a regular hexagon, then all sides have the same measure. They're all equal to each other. So you can see there, they have drawn one line of symmetry through all the vertices. So that's 3 lines of symmetry. And then they have a line of symmetry through all the midpoints. It would also work if they folded it over those. So there are 3 through the vertices, there are 3 through the midpoints, to give 6 total lines of symmetry. Okay, so now let's look at these two. So, are these regular polygons?
No.
No, all the sides are not equal, right? So, because it's not regular, it may not work exactly like this. But for anything that's regular, you can go through all the vertices and all the midpoints. But here, maybe
Two
you can't.
lines. 2 lines.
2? Where are they?
Horizontal or vertical.
So, a horizontal line through the midpoints. Here. And a vertical line
There's
through
2.
the midpoints here.
If you do like it, if you do from the top left corner to the top, to the bottom right corner, and the top right to the bottom.
No,
left.
because the shape would
Like
not
one of
work.
those finger rows.
You think here?
No. Disagree. I disagree.
Okay, so what does a rectangle kind of look like? A rectangle is kind of similar to a piece of paper. So if I fold it along those corners, like what you're saying,
No.
does it line up exactly on top of the other side? No, so I know in our heads we think, well, I look like I could cut it in half and even, but again, line of reflection, you have to fold it and it work exactly right. So the corners like that will not work for a rectangle. So you think about the trapezoid in B and see how many lines of reflection you think it'll have. Yes, hello.
I see two.
Two.
Horizontal and vertical.
Oh, you didn't know I taught? Yes. Whatever will match your level of dressiness. I would choose, just get that blue pullover right there. Yeah. Okay.
Oh, yeah.
Okay, so how many did we see on B part?
Two.
One.
Two.
Megan, you are false.
Oh, wait.
It's one.
Where?
It's just vertical. That's the only one that fits.
Oh, yeah.
Vertical right here?
Yes.
Oh,
If
yeah.
I fold that over, will it fold
No.
exactly on top of
Yeah.
itself?
Yeah.
That will. Alright, why will this one not work?
Because they're not
Top's
even.
smaller than bottom.
Top is smaller, right? So if you fold that over, it's not gonna line up exactly. So, very good, this one only has one line of symmetry. Okay. Questions there?
No.
What we're doing?
It's so easy.
Easy? Good.
Easy square.
Of rotation, does the figure map onto itself? So then we're looking at an equilateral triangle, and then we're looking at a parallelogram. So basically what they're asking is, okay, if I rotate this figure, how many degrees do I have to rotate it before it maps exactly on top of itself?
180.
120.
So the parallelogram, let's do that one first. I think that one's easier. Look at the parallelogram first, okay? If you rotate that 90 degrees, so imagine turning it straight up and down, is it gonna line up exactly
No.
with itself?
It's going to be 180.
No. If you do 180, will it line up exactly on top of itself?
Yes.
It does. So a parallelogram has 180 degrees rotation, and if I do another 180 degrees,
It'll be back in the spot.
so that's all of it, right? There's no more you can do. Okay, but if I think about the triangle there. All right, let me take another picture of the triangle.
Bruh.
Okay, so here's my triangle. If I rotated it, because it's equilateral and all sides are equal, can I rotate it here to make it match?
Yes.
So I've rotated it one time. And if I keep rotating it, does it line up again?
No. Yes.
Yes.
Yeah, have I done a full circle yet?
No.
No. And then two times. And then if I rotate here, can I line it up? Yes, but that is back to the way it was lined up to start with, right? So it does,
No, these aren't going to block. Two rotations.
right, it has 3 times it matches within 360 degrees. So think about here, because again, these are easy for us to think about. We could rotate it 180, and then we could have rotated it 360 and lined it up. Right. So within that 360 degrees, it mapped onto itself twice. So if I do 360 divided by 2, that means I just had to rotate 180. But we know what a 180 looks like, so that's easy to do in our heads. But a 120, I mean, how do I know what 120 is in my head? I mean, it's hard, right? It's a little bit more than 90, but I mean, how am I going to get exactly 120? So we do the same math. It mapped onto itself 3 times within 360 degrees. So we'll do 3 divided by 360, which is 120. Which means every 120 degrees, it mapped on top of itself. Okay? Think about with a square. What if you were rotating a square? How many times does it map on top of itself?
Twice. Oh, 4.
4 times, right? So how much do you rotate every time?
120.
No.
180.
No.
90.
90. Because if it's going to map on top of itself 4 times, 360 divided by 4 gives us 90. And we know what a 90-degree rotation looks like, right? If I take it from here and rotate it 90 degrees, I'm going to be right back on top. And then another 90 degrees, right back on top of itself. So let's see if this pattern, what do you think about a pentagon? If I had a regular pentagon.
You would have to go 180. No.
Dang,
You have to go 360 to get it to be on top of it.
Yes, so for this one, yes, you're right. That's all the way back to 360. But so, something to think about, if it has symmetry, like this one, right? So like how many times will this map onto itself in one full rotation? So if I pull this end up to the top,
4.
it would map onto itself. If I pull this one up, 2. If I pull this one up, 3. And then all the way around is 4. So it maps onto itself 4 times within 360 degrees. So we can do 4 divided by 360, which means I only have to rotate it 90 degrees. Right? And then what about B part? It's a little bit oblong.
2.
Then that make it 180 since it's oblong.
It is 180.
You do it
Right.
horizontally.
Right, you'd have to go all the way a full turn, 180 degrees before it lined up. So it would only map onto itself twice within 360 degrees, which means it's at 180 degrees. So I just have looked at it again. The question is not how many times does it happen. The question is how much do you have to rotate it. So, no. Right here, we said it would happen 4 times, right? Which we found to be 90 degrees. That means every 90 degrees it maps on top of itself. So that's going to give me 90, 180, 270, and then we don't count 360, right? Because that's all the way back around. So it would be 90, 180, and 270. And then here we talked about it would be 180, and then 360. We don't count 360. Okay, that's the kind of answers they're looking for on those. When they're asking, what are the rotational symmetries? That means how much did we rotate to get there? Okay, here. We want to know what type of symmetry does each figure have. So right now we're looking for rotational symmetry and reflectional symmetry. So when you look at that flower, let's first look for the reflectional symmetry. How many lines of reflection can I draw? Well, is it a regular shape? Are all the sides the same length?
No.
I don't know, it's close, right? It's hard to tell.
2 bottom ones look,
Longer?
yeah, they look a little bit different than
Okay? So, let's see, you see they drew a line through each point in my flower. So there was one line drawn here, then right here's the second point. 2, 3, 4, 5, but then we've already counted this line, right? So you don't count it again, because it was part of this one. So we had 5 lines drawn, and think, if I folded over all of those lines, will it fold on top of itself? If I fold over 2, it does. If I fold over 3, it does. If I fold over 4, it does. Okay, it's hard to imagine because when you fold over this, it's folding this way, right? So this piece is going to line up with this one. And then this one will fold on top of this one, and then this one's divided in half. Okay, so those are kind of hard to see. So there are 5 petals, that means there are 5 lines of symmetry. You see that? A line through the center of a petal is a line of reflection. Because there are 5 petals, there are 5 lines of symmetry. Now then, the rotational symmetry. This time, think about how many times it could rotate. We could rotate 1, 2, 3, 4, 5 times within 360 degrees. So what they did is you take 360 divided by 5. That means every 72 degrees you rotate, you get somewhere it lines up. So that would be at 72. Then if I add 72 again, that's 144. If I add 72 again, 216. Add 72 again, 288. If you add 72 again, it's 360, which we don't count. Because that's all the way around. Alright? And then
So we basically gotta add up everything to 360.
yes.
Okay, that's easy stuff right there.
So right here we've got a card here with red points on it. Very odd looking card. So can I draw any lines of symmetry that if I fold it over it's exactly on top of itself?
Yes.
Where?
Oh, wait.
Well, if I fold it this way,
No.
that would work if it wasn't for the red point.
Yeah. So no.
The red point's gonna be in the wrong place, so that doesn't work. What about this direction? Can I
No.
fold there?
No.
Actually,
No, that doesn't work. And then, again, if you look like,
You can't do that because it's uneven.
exactly, kind of like the paper, right? So if there was some way we could draw through this point and through this point
There's-
and through the corner,
There's no
it's
line
not
of
just
symmetry.
a line, right? It's a lot of different lines.
There's no line.
Coach Goose, I don't know if it would work, but I'm looking at it, Joey, but if we did it horizontal, and then once it's folded horizontal, you fold it vertical.
You can't do 2 though. So for a line of symmetry, it has to be one reflection,
There's
one
no,
line.
There's
Is
no
that
line
what
of
we're-
symmetry.
Yes, you're right. If I folded it over, and then if I could reflect it,
Like across
the diagonal. So it's kind of the same thing we were talking about with the paper. Because it's not a rectangle, then to go from here to here, when you fold it, it's going to be mismatched. This is going to be over here, kind of like when I folded that paper. So the diagonals don't work unless all the sides are the same. If it's regular, like a square, or a triangle, where all the sides are the same. So it has no lines of symmetry. Okay, but can I rotate this card to make it line up with itself? So what if I rotate 180 degrees? Think about where the red dots would be. So this one, if I rotate 180 degrees, would go. And if I rotate this one 180 degrees, it would go. So that works, right? They swap places. So it does have rotational symmetry of 180 degrees. If I rotate 180 degrees, it'll be exactly back with itself. So it has no reflectional symmetry, but it does have rotational symmetry at 180 degrees.
You going in the game
Still under.
Okay? So how many lines of reflection are there?
4.
4 lines of reflection.
2 lines.
Where are they at?
Horizontal, vertical, and from corner to corner.
Okay,
Can't
so
do
you
corner
got
to
a
corner.
horizontal
Yes, you can for a square.
line of reflection. You have a vertical line of reflection.
Oh, I did have 4 on there.
Rectangle.
And then we have from corner to corner.
You can't for a rectangle, you
Can't
can
go
for a
across.
square.
Wait, 1,
Correct.
2. So that's 5, right?
That's 4.
1,
Right here is 1, 2, 3, 4. This line is part of line 1.
Oh, I was counting
This
all.
line is part of line 2. This one is part of line 3. This one's part of.
Maybe this is my head.
I know, I agree. That's why you got a number like that. So there are 4 lines of reflection. Now, how much rotational symmetry does it have?
4.
It happens 4 times within 360 degrees.
So, and the
So that
degrees.
means how much do I rotate every
90.
time?
90.
So what are my rotational symmetries? 90,
9.
180,
220.
270.
7, sorry.
And then 360 gets me all the way back, so I don't count it, right? So 90, 180, and 270. So there are 3 different rotational symmetries.
So on a, like if it was on a test or something, would you put 3 or 4 rotational if you don't count the last?
This is what it wants.
Just 3?
It wants 90 degrees, 180 degrees, 270 degrees. This is what it wants on the test. When it asks for the rotational symmetry, it's going to say you can rotate it 90 degrees, 180, or 270. That's really how you're asking.
But you wouldn't put down the 360.
Correct. Because 360 is what it started with. So if something only has rotational symmetry after 360, then it doesn't have it. Because that means the only way it maps onto itself is by rotating all the way around. Let me get my little sticker here. He can't map onto himself unless he goes all the way around. So he doesn't have rotational symmetry. So 360 is kind of useless.
It's kind of sus.
Everything rotates 360 onto itself. Kind of sus. Yeah. Guess you could say that.
Of course, Gracie.
Anything else here on this one? All right, that's it.
It seems like this would be the easiest section of it.
It is.
For today. We haven't just left it.
So on Monday, we're going to work these problems. Maybe grade them before the end of class. That'd be nice. Tuesday, practice test.
Wednesday test.
Wednesday test will be our plan.
And Thursday, Friday, day off?
No.
Yes.
Thursday we're off.
Thursday.
Thursday's Veterans Day.
Oh, we had a professor day.
Thought we were out Friday too.
No, just Thursday.
Now you're thinking.
We're at school Thursday.
Bryce, you do, work.
Dang, you asked me this earlier.
Hey, the direct objects test is just like the lesson practice.
Well, some of us don't have to take it.
Without.
The whole place don't have to take it if you have a class you want to go off.
It's a book.
It won't surprise me if she makes you already take it. Y'all miss it?
It's like business.
She makes people miss it. Just what? The test. If she makes people retake the test, she should make anybody who misses it retake it. I'm not against sports, but I'm that way it's not be fair to somebody.
Oh, you can always correct the writing, it's not a stupid form. Yeah, I was going to. Oh, yeah.